Hello everyone, welcome to the session. In this session, we are going to find out the frequency of AC, that is alternating current. If I introduce you the current, we have the classification like the direct current and the alternating current. So the direct current, the source of direct current, let us say a battery or a cell which gives the steady current which is not going to change with respect to time. And we have the other part, the alternating current. This and very important one, which changes with respect to time. You see, the alternating current is having more advantages compared to the direct current. That means we can transmission of AC current can be done easily. We can increase the voltage using the step-up transformer, and also we can reduce the voltage using the step-down transformer as per our requirement. So now, in this session, we are going to find out a factor related to the alternating current, that is frequency. The frequency with which the alternating current changes its direction. So that's our aim. For this experiment, the operators used are: the first one, the sonometer. It's a device, the name itself suggests us that sono refers to sound, meter refers to measurement. Basically, we use this instrument to measure the sound, the factors related to the sound. So sonometer, which has a stretched string, and an AC source, which the range is of 6 volt, which uses a step-down transformer. Basically, we receive the current and voltage at a range of 220 to 240. So, which uses a step-down transformer, which reduces it to 6 volt. So, AC power supply. And we use the slotted weights with hanger, each of 500 grams. And electromagnet. When we pass current through it, we have copper wires mounted over a soft iron. When we pass the current through it, it behaves like a magnet. Connecting wires and stand to fix the electromagnet over the stretched string. Stand we have. So these are the operators used in the experiment, frequency of AC. Let's move on to the principle. Here, at resonance, the frequency of alternating current is equal to the half of the frequency of vibration of stretched string. One way of explaining it. So, I would like to place it in my own words that resonance means we apply a frequency using this AC source. We apply a frequency for the stretched string. When this frequency is equal to the natural frequency of the stretched string, of the experimental string. So this string is going to oscillate with maximum amplitude. So you can see a loop which will be formed in this stretched string at resonance. It will happen at resonance. So the principle used in this experiment is resonance. The applied frequency is equal to the natural frequency. So the formula, frequency of alternating current, we have F is equal to 1 over 4 into square root of m into slope, where m refers mass per unit length of the string. So how we can calculate, just taking an 1 meter of wire and calculating its mass, so mass by length, so that we get mass per unit length. The mass per unit length of this experimental wire, what I am using is 1.25 into 10 to the power minus 3. Little bit slow. So by finding out the values of tension and the resonating length, so we need to plot a slope L square versus T. This formula is actually obtained from the fundamental mode of vibration of a stretched string. So an updated version, I can say F is equal to 1 over 4 into root m slope is an updated version of the formula for stretched string. So now let's move on to the experimental procedure. Yes, let's start with the experiment. We have the stretched string. Each time I will apply a tension for that. For the first time I am applying 500 grams of mass, which includes the anchor. So each time 500 grams, I keep on increasing. The resonating length, that is the vibrating length, also changes. So first we'll start with the 500 grams weight. I fix this electromagnet at 50 centimeter on the sonometer board. Let's connect it. So you can able to see the loop when the applied frequency from the source is equal to the natural frequency of this stretched string. Now I am going to move this knife edges. Let's maintain a distance of maybe some 0.5 centimeter between the electromagnet and this wire. At resonance, starts vibrating. Yes. Yeah. So you can able to see the bigger loop. That means at resonance, this loop will be of maximum amplitude. So what happens is this applied frequency is equal to the natural frequency of this stretched string. So I'd like to find out this length. Yes. So it is 68 minus 35. So 68 minus 35, we get 33 around. Next, I'm going to increase the tension. I'm adding up another 500 grams of weight. So now it becomes 1 kg. As the tension increases, the resonating length also changes. Of course, the resonating length also increases. So I'm changing the distance. Yes. Okay. So at resonance, it starts oscillating. Yeah, you can able to see the loop which oscillates with maximum amplitude. So this comes out to be 75 minus 29.5. The process continues. Now 1.5 kg, the mass is added. You can see there is no loop, resonance is not happening now. So again I change the distance. I'm increasing the length of the wire. Yes. Yes. So at a particular point, only the frequency, at resonance only the frequency matches, the applied frequency matches the natural frequency. There only you can see the loop. It will be oscillating with maximum amplitude. So here it is 80.5 minus 24.5. So add up another 500 grams. You see there is no loop. Let's change the distance. The length changes. Yeah. So this value for 2 kg, 85.5 minus 20.5. Okay. The last value 2.5 kg, 5 readings I am going to take. Yes. Okay, so this is 90 minus 16.5. So we got 5 values each time. We increase the tension, so the resonating length also changes. The basic idea is that the tension is directly proportional to the resonating length. As the tension changes, the resonating length also changes. So I am talking about resonating length, that will be between two knife edges. You can see between these two gaps, this stretcher string is vibrating. So this length from this point to this point is called resonating length. Let's go for the calculation part and find out the frequency. Here is the tabular column for what we have performed the experiment. Each time I have changed the mass is 0.5, 1, 1.5, 2, 2.5. For that, the tension, corresponding tension will be 0.5 corresponds to 4.9. That is, tension is equal to m into g, the acceleration due to gravity 9.8. So 0.5 9.8, 4.9. So in the same way, we have the tension 4.9, 9.8, 14.7 like that. For which the resonating length corresponds like this. We got it in centimeter, and here we have converted into meters. So the resonating length stands like this, and actually we need L square. The square of this resonating length in meter square we have mentioned here. So now I am going to plot the graph for this tension and resonating length. I am making use of these two things. So the graph along x-axis I have taken the tension, and along y-axis I have taken the square of the resonating length. So here I am going to write the scale first. X-axis 1 unit is equal to 4.9 Newton. 1 unit is equal to 4.9 Newton. Y-axis 1 unit is equal to 0.1. By looking at the values, we need to take those. 0.1 meter square. Y-axis, I am taking the square of the resonating length, 0.1 meter square. Now for the first value, I write the values here. So this is 4.9, 9.8, 14.7, 19.6, 24.5 values, and the corresponding L square values For that I have 0.1, 0.2, 0.3, 0.4 and 0.5. You can take more 0.6. Actually I need it up to 0.5. So first one, 4.9 is equal to 0.1089 and I am getting the rounding it off to 0.10. So 4.9 which will be somewhere here. Next 9.8, for that we have 0.2025. So 9.8 will be this one. And then again 14.7 we have 0.3136, so which corresponds to somewhere here. So 19.6 like way 24.5 we have 0.53. So let's draw all the points. We get a straight line. So we get the graph. So what we need to calculate here, the slope. L square versus t, we get a straight line. Let's find out the slope of this one. I join this point. So let's call it as A, this is B and C. So we want the slope of the graph. Slope will be equal to AB by BC. So AB, the value you can see, this point corresponds to 0.4 and the B corresponds to 0.2, so which we get 0.2. BC, so the point B corresponds to 19.6 and C here corresponds to 9.8. So 19.6 minus 9.8, it has 9.8. And finding out the slope, we get as 0 to 0. So we get the value of slope as 0.020. Let's calculate the frequency of the AC. For that we have formula F is equal to 1 over 4 root m into slope. So F, which is 1 over 4 root of m, that is the mass per unit length of the string, 1.25 into 10 to the power minus 3. The slope we get it as 0.020. Let's solve this. F is equal to 1 over 4 root of 1.25 into 10 to the 0.002. 0.025 into 10 to the power minus 3. So make certain changes here. F is equal to 1 by 4. I write this one as 25. I am shifting 3 points. 1, 2, 3. After decimal point I am shifting 3. So 3, we already have 10 to the power minus 3. So it becomes 10 to the power minus 6. And taking square root, F is equal to 1 by 4 into 5 into 10 to the power minus 3. So 10 to the power minus 3, shift upwards. So that is 1000. 1000 by 4 into 5, 20. So finally we get F is equal to 50 hertz. Yes, we got the frequency of AC as 50 hertz. Actually, there's a what we get the supply as the source. So here I have an AC motor, so which converts the mechanical energy into the electrical energy. And I move this. So what actually happening here is the rectangular coil kept between the magnetic field. When this rectangular coil moves, so the current will be generated. So 50 oscillation, which one is moving here? Here this rectangular coil, when I rotate it, so in a second it might give 10 rotations. So I can say the frequency as 10 rotations per second. The frequency will be number of rotations per second. So this rectangular coil, if it rotates 50 rotations per second, I can say the frequency of this current generated is 50 hertz. In most of the cases, so that's what I would like to prove, that why it is exactly 50 hertz. In most of the cases, basically what happens in thermal power plants, nuclear power plants and hydroelectric power plants, the magnetic field will change. The 50 hertz means the magnetic field in 1 second it will oscillate for 50 times. So that's why we receive an AC source of 50 hertz. So it's matching our results here. We can able to find out the frequency of alternating current as 50 hertz with the help of this sonometer and an electro